Hello, and welcome to the Computing Conversations column. This column is from the April 2017 issue of IEEE Computer and is titled Resurrecting the CDC 6500 Supercomputer. There is supporting video material for this column that you can find in the IEEE Computer Society YouTube channel or in the IEEE Digital Library. I'm the editor of the column, and I'm Charles Severance from the University of Michigan. Living Computers Museum and Labs in Seattle, Washington is filled with historically significant computing technology that remains powered up so visitors can experience firsthand what computers looked and felt like decades ago. The museum, founded in 2005 by Paul G. Allen, has the largest collection of working and restored computing machines. Walking past the many micro and mini computers into the back room with the raised floor, you can see one of the world's first generation supercomputers, the CDC 6500, which fills several refrigerator-sized cabinets with electronics, wiring, and liquid cooling. Manufactured by the Control Data Corporation and designed by supercomputer pioneer Seymour Cray, the CDC 6500 was first announced in 1964. Building the CDC 6500 pushed the available technologies to their limits. It was expensive to purchase and maintain and had tens of thousands of custom parts and circuits. There were very few CDC 6500s built, and each system cost millions of dollars. Those that were built were only available to the government, research labs, and well-funded universities. At the time, the CDC 6500 was so powerful that it was considered a national asset and was thus illegal to export for quite some time. In 2013, Living Computer Museum and Lab acquired a CDC 6500 that was built in 1967 and ran at Purdue University until it was decommissioned in 1989. Some electronic parts were pulled out and melted down for their gold content, and the chassis were disassembled using large wire cutters, pipe cutters, and crowbars to get the unit out of the machine room. It seemed impossible to resurrect, but the museum pulled it off. During my visit there, I spoke with principal engineer Bruce Sherry about what it took to bring this machine from a salvage to production. When they acquired the CDC 6500, they began the process of restoring it so that it could once again run in production. All of the connecting cables between the cabinets were cut when the machine was disassembled.
This machine was 22 years old when it came out of service. And all these cables that you can see here were cut. And so the first thing we had to do was get new cables for the machine. Now the cable was manufactured by 3 different companies, and none of them would make us a cable of the ones that were still in business. So we had to go searching. One of the things we needed for the cables was the taper pins that go on the end.
The pins were manufactured by AMP, which was still in business. They had taper pins in gold or tin, but not the silver that was required for the CDC 6500. With a bit of convincing and negotiating and LCM's promise to purchase 50,000 pins, AMP agreed to produce a limited run of silver pins.
So we talked to them, and we talked to them, and eventually they said, all right, well, if you buy 60,000 pins for $1 a piece, we'll make some for you. And we said, okay, and they kind of were startled, and a few weeks later they came back and said, gee, we don't have enough material to make 60,000 pins, we're sorry, but if you take 50,000 pins at 75 cents a piece, we can do that. And we said, okay. So I have 40,000 pins sitting upstairs on the shelf because I only needed 10,000 to put the machine together. That was $60,000, and then we spent another $60,000 to actually make the cables with the pins on the ends. And then it took about 5 weeks for my technician to replace all the cut ends with the new cables, which is really kind of amazing because he only made 2 mistakes in that whole process.
Once the chassis were reconnected, the next challenge was to bring the cooling system back up.
So this is the first machine that was cooled with Freon. You might be able to hear a little humming in the background in amongst all the noise that the rest of the computers make. It's kind of a sound. And that's the compressors for the refrigeration system that cools it. So here's our refrigeration system. Each one of the 3 bays has one of these refrigeration systems in it.
The chilled Freon is pumped through small copper tubes so that every one of the logic modules is separately cooled.
We compress it into a liquid with the compressor here. The liquid goes through this heat exchanger to move the heat into water. The water goes up to a water chiller on the roof, another $185,000 just to install that guy. And then he runs it through hoses, and you can see these hoses here going into each of the 12 chassis.
The chassis contain electronic logic modules with transistors, resistors, and capacitors to implement the CPU and peripheral processing units. Memory storage is provided using 170 core memory modules, each of which is about a 6-inch cube.
Each one of these little blocks is 4K words by 12 bits, and for the main CPU there's 5 blocks to make the 60-bit word of the computer. So this chassis holds 16K words, and we've got 8 of those for a total of 64K words. Actually, it's 128K words in the whole machine, but I only have half of it working.
It is challenging to keep the memory modules running. They consist of a woven mat of core memory with fine wires running through the cores to read and write the data that is stored in each core. It is difficult to repair the core memory because everything is so small.
There's 12 of these core mats inside here, stacked in like this. Here's the core mat. There's 4,096 bits there, and each thing that looks like it might be a circle is actually 4 cores on edge, and each core has 5 wires going through it. And they're all supported by the wires that go through there.
Because the logic modules are made up of separate transistors, resistors, and capacitors, it's sometimes possible to repair a failing module.
But here you can see on the edge, these little silver cans are all individual transistors. So your phone has about 1 billion transistors in it. This whole machine has about 250,000 or so. And if the transistor is on the edge, I can change it because amazingly enough, I can still get the transistor. The package is a shortened version of the TO-18, and I can get the standard part just off the shelf at DigiKey these days.
When it's impossible to find a replacement for a component, the Living Computer Museum and Labs switches into laboratory mode to design and build a new component from scratch. The new component must meet all the physical, size, and power and logic requirements of the existing module, but can use modern parts. Bruce and his team were recently able to reverse engineer and construct a replacement for one of the CDC 6500's logic modules using modern technology.
As of yesterday, I have managed to actually build a replacement for one of these modules. So the new module I've replaced uses the surface mount version, which I can also get, and I put the transistors on the outside when I did it so I can change them should I have to fix that module. But it was really a nightmare putting them back together because you have to put all the resistors and diodes in on one side, and then you try to slide them across and get them into the right hole on the other side. And it's a rather tedious process, but it works. So that's what they did then.
Once the CPU and memory were working, it was time to try and load the software onto a computer and test whether it worked. They didn't have enough hardware to load the operating system onto the CDC 6500.
When we got this machine, we got 3 peripherals. We got a card punch, but no controller, which is a much bigger box than the card punch. We got a printer, but no controller, which is the same size as the printer. And we got a tape drive, but no controller.
Without the controllers, there is no way to plug the hardware into the CDC 6500. So Bruce and his team used a Windows PC with a set of 6 FPGA cards to emulate the CDC controller hardware and peripheral hardware.
So in order to bring the machine up, if we walk around here, I had to design emulations for most of the peripherals here. And that's what I've got in this rack here. Each of these silver guys is talking to one channel from the CPU. And so the first thing I had to do was emulate the dead start panel, which was we would call it flash or read-only memory these days, but it gave me 12 instructions to boot the machine with. And that wasn't much to run diagnostics out of. And so I emulated that so I can put in a 4,000 word program, which is as much as our peripheral processor can hold. And that allowed me to do a lot of diagnostics. Then the next thing we had to do was the display, because our real display, A, the one for this machine doesn't work yet after 2 years, and B, they're very fragile. We left the one we have on over the weekend one time, and a transformer blew up, and it took about 4 months and $15,000 to get a new transformer built. After we got the display, then we had to emulate the tape drive, and then we emulated card reader and card punch, and then a line printer, and all those things are running now.
The emulated console looks very much like the original CDC 6500 with its soft green vector graphics and characters that flickered as the CPU communicated with the peripheral processors. Bruce compiled and ran the LinPack benchmark to give the computer something to do. It took 6 seconds for the CDC 6500 to compile the code stored on the emulated disk drives, and then executed for 45 seconds on the real CDC 6500 CPU. It was a privilege to talk to Bruce and explore the history of the CDC 6500 restoration. I used punch cards to run Fortran programs on a CDC 6500 at Michigan State University in the late 1970s. By the mid-1980s, I was a professional developer supporting faculty use of the CDC 6500. I spent plenty of hours sitting at that green glowing CDC 6500 console as an operator mounting tapes or debugging system issues. For me, spending time with Bruce in the CDC 6500 was like a 40-year class reunion. This column is from the April 2017 issue of IEEE Computer and is titled Resurrecting the CDC 6500 Supercomputer. There is supporting video material for this column that you can find in the IEEE Computer Society YouTube channel or in the IEEE Digital Library. I'm the editor of the column, and I'm Charles Severance from the University of Michigan.